created by Mindstakes Foundation Trust. Welcome to today's masterclass on geometrical constructions. We are going to explore 3 essential methods for constructing tangents to a circle. We will cover using the center, working without the center, and finally, constructing a tangent from a point completely outside the circle. So, keep your compass and ruler ready, and let's begin. Our very first topic for this explainer is constructing a tangent when we actually know the exact center of our circle. Before putting pencil to paper, we really need to understand the core geometric property that makes this all work. There is a fundamental rule. A line drawn perpendicular to a radius at its outer end is always a tangent to the circle. This simple, absolute guarantee of a 90-degree angle is basically the secret engine driving our first method. Let us look at the theoretical blueprint. Suppose we want to construct a tangent, let's call it line L, that passes through a specific point P on a circle with center C. If we draw the radius CP, well, for line L to be a true tangent, it absolutely must be exactly perpendicular to this radius at that outer point P. So our entire goal here simply boils down to constructing a perpendicular line at a specific point on a ray. Let me slowly and deliberately walk you through the practical steps. Step 1, you just draw a circle with center C and take any point P on its boundary. Step 2, for our convenience, draw a ray starting from C, passing straight through P and extending outwards. Let us call this ray CX. And finally, step 3, using your compass, construct a line L that is strictly perpendicular to ray CX, ensuring it passes exactly through point P. Once done, you will notice those small compass arcs cutting the ray on both the left and right sides of point P. From those 2 new points, we draw larger intersecting arcs above and below the line. By joining those intersections, we lock in a perfect 90-degree angle at point P, creating our required tangent perfectly. That first method is quite straightforward, isn't it? But here is a critical thinking question to ponder. What if we do not have access to the center of the circle at all? Imagine someone just gave you a circular bangle, trace it on a paper, and ask you to draw a tangent. The center is completely hidden. How exactly do we proceed then? Well, mathematics always provides a way. This brings us nicely to our second technique, constructing a tangent without using the center. Because the center is missing, drawing a radius is out of the question. Instead, we have to rely on a beautiful geometric concept known as the tangent-secant angle theorem. This theorem tells us that the angle between a tangent and a chord is exactly congruent to the inscribed angle located in the alternate segment. So, practically speaking, if we can perfectly replicate an inscribed angle using our compass, we will automatically generate our tangent line. To visualize this, if we want a tangent at point C, we first draw a chord CB. This chord naturally creates a major segment inside which we draw an inscribed angle, angle CAB. According to our theorem, if we draw a line CD starting from point C in such a way that angle BCD is perfectly equal in measure to angle CAB, then line CD is absolutely guaranteed to be our tangent. Please pay very close attention to these 5 precise compass steps. First, draw your circle and mark point C. Second, draw the chord CB and any inscribed angle CAB. Now step 3, place your compass needle on vertex A. Take any convenient radius and draw an arc that intersects both sides of angle BAC, naming those intersection points M and N. Step 4, without changing that compass radius, move the needle to point C and draw a large arc that intersects chord CB at a point we will call R. Finally, step 5, measure the exact distance between points M and N with your compass. Place your needle on R and cut the large arc you just drew. Let's call this final intersection point D. By drawing a straight line passing through point C and our new point D, we get our beautiful tangent line. And why does this trick work? By copying the exact arc lengths with our compass, the imaginary segments MN and RD would make triangle AMN and triangle RCD perfectly congruent by the side-side-side test. Because the triangles are congruent, angle CAB is exactly equal to angle BCD, just like magic, but it is pure logic. Excellent work so far. We have successfully drawn tangents from points lying exactly on the edge of the circle itself. But let me challenge you a little further. Can we draw a tangent from a point sitting entirely outside the circle? If our starting point, P, is far away in the exterior, how on earth must our approach change? This brings us to our final and perhaps most fascinating construction method, drawing tangents to a circle from an exterior point. To solve this puzzle, we will use a very elegant theoretical trick from your earlier geometry studies. We know for a fact that an angle inscribed in a semicircle is always a right angle, exactly 90 degrees. We desperately need 90-degree angles between our tangents and our radii. So if we can strategically draw a second circle with a very specific diameter, it will automatically create those crucial perpendicular intersections for us. Picture our circle with center O and a point P sitting way out in the exterior. We wish to draw tangents PA and PB. If we simply join the center O to point P, the segment OP becomes the hypotenuse for two right-angled triangles, OAP and OBP. Since those angles must be 90 degrees to form tangents, points A and B will naturally lie on the circumference of a second circle that happens to have segment OP as its diameter. Let us walk through the practical steps to make this happen. Step 1. Construct your circle with center O and mark your exterior point P. Step 2. Draw a straight segment connecting O to P. Now, step 3. We need to find the exact midpoint of segment OP. So we draw a perpendicular bisector of segment OP. Let us call this midpoint M. Step 4 is where the real magic happens. Placing your compass needle exactly at midpoint M, take the radius as OM and draw a second circle. You will clearly see the perpendicular bisector finding the midpoint M, from which the second circle is drawn. The specific points where this second circle intersects our primary circle are our golden points, A and B. By drawing a line from P straight through A and another from P straight through B, you have successfully constructed your two exterior tangents. It is a really satisfying result. To wrap up our masterclass, I want to leave you with a thought-provoking question drawn directly from your problem set. Think critically about the geometry we just explored together. What is the absolute maximum number of tangents that can be drawn to a circle from a single point located outside it? If you recall those intersections A and B we just found, the answer is right in front of you. Keep practicing these constructions, and you will master them in no time.